All right, let's integrate a function over a general region. So the last section was all about integrating functions over rectangles. Now we can integrate functions whose domain is bounded by continuous functions. So let's work on example 16.2 here. I want to find the volume underneath a function that lies on top of a triangle bounded by the lines y is equal to 0, y is equal to x, and x is equal to 1. So 100% of the time, we're going to draw the region. So I've got this function that's existing over a triangular region in my plane, right? Because this is a function of 2 dimensions. All right, so if this is x and this is y, then the region that I want to integrate this function over is bounded by the lines y is equal to 0, y is equal to x, and x is equal to 1. So the region bounded by these lines is this region here. All right, so if I tilted this and I were to go into 3-dimensional space, which is where my function lives, this is going to be x, that's y, this is the z-axis or the outputs of my functions, then I'm looking at this triangular region in my xy plane, and then on top of this region is my function. In fact, my function is a plane, so it's going to be more of a straight line. All right, so it's going to be some sort of plane. And then I want to integrate over this triangular region. Okay, so this is the region that I want to integrate over. So I want to perform the integral of f of x, y, dA over that region R. So this is my region R. Now, by Fubini's theorem, this is a continuous function, so I can take this multivariable integral iteratively. So I can integrate in one dimension, and then I can move on to the integral in the other. And I can also do this in any order, and we're going to do both orders in this problem. So if I integrate, let's say we integrate with respect to y first. So if I integrate with respect to y, I'm going to draw a little line up and down in the y, and that line represents the integral in the y. So I'm going to integrate my function in y first, and this line right here, what are the bounds of that line? The bottom is going to be y is equal to 0. The top is going to be y is equal to x. At that point right there, all of these lines are going to have bounds y is equal to 0 and y is equal to x. And then I'm going to take these lines. So that integral right there gives me these vertical lines. And then I will integrate those vertical lines. So I'm going to give myself an infinite number of them, and that's going to fill the volume. So those lines are going to run from x is equal to 0 to x is equal to 1. Okay, let's go through this. So when we perform the first integral, I'm going to leave the outside integral alone. And the first integral is going to be, actually, let's just write down the function. 0 to x, 3 minus x minus y. Integrate with respect to y first, and then the x. When we perform the first integral in the y, it is going to be 3y minus xy minus 1/2 y squared, evaluated between y is equal to 0 and y is equal to x. Okay, so when we do this, we're going to get 3x minus 3x squared over 2, which we will then integrate in the x. So this right here gives me the lengths of these vertical lines that we've drawn. And I'll take those vertical lines and I will integrate them across the x direction to fill my space. So when we integrate this with respect to x, we're going to get 3x squared over 2 minus x cubed over 2, evaluated between 0 and 1, which I guess to keep with this pattern, I'll say that x is equal to 0 and x is equal to 1. All right, so when we do this, we end up with a volume of just 1. Okay, let's do the exact same thing, but integrate in the opposite direction, or in the opposite order. So I'm going to clear off that picture. In fact, I think I'm going to pause and then erase everything, so that way I'm not wasting time. All right, now let's find the same area. So let's draw the region. This is the triangle that I want to integrate over. So the integral over the region R of my function, because it is a continuous function by Fubini, I can iteratively take my integrals. And this time, let's integrate in the x first and then the y. So if I integrate in the x first, my lines are going to be horizontal. So the length of that line is going to be the result of my first integral. All right, so my bounds are going to be between this line here and this x value of 1. Now, when I think about writing that point right there, I can't say y is equal to x, right? I don't want to have an x down there because this integral is in the x. And you can't have your bounds share the same variable as the variable of integration. That doesn't make any sense. But if that line is y is equal to x, then x is equal to y. So I'm going to integrate from the y value over, or sorry, the x value that's equal to y here over to the x value that's equal to 1 right here, right? That gives me my horizontal lines. So this integral gives me my horizontal lines, and then the second integral will integrate those horizontal lines to fill the volume. So the y's need to run from y is equal to 0 to y is equal to 1. All right, so by Fubini's theorem, we should get a 1 out of this as well. Let's make sure that we do. Let's just first copy everything down and tell ourselves what the function is. All right, if we integrate in x first, we end up with 3x minus 1/2 x squared minus yx, evaluated between x is equal to y and x is equal to 1. All right, now when we do this integration, the first integral, we're going to get a 3 minus a 1/2 minus a y minus 3y plus y squared over 2 plus a y squared. Okay. Let's go ahead and clean that up before we integrate, make it easier on ourselves. This is going to simplify as 5 over 2 minus 4y plus 3/2 y squared, which when we integrate in the y variable, we're going to get 5/2 y minus 2y squared plus y cubed over 2, which we will evaluate between y is equal to 0 and y is equal to 1. Now, when you do this, you get 1, which is what the other order of integration told us.